Alright, so recording has started, and let me take you to the practice quiz and problem number 1. And it asks you to take this derivative two different ways. One is the way that I taught yesterday, which was, the simplest way to do it. And then the second way is to do a u substitution. It even tells you what the u is, and then to use this form of the chain rule right over here. So let me give you a little time to do number 1 both ways. Alright, does anybody need more time doing it the first way? Alright, so let me show that. dy dx. 5 times the 2 is 10. And then decrease this power by 1. And then we have to chain on the derivative of the inner function. 14x minus 3. And then the 14x minus 3 and the 10 could all be put, up at the front if you wanted, but even this would be fine, leaving it like this. Alright. You should be getting the same answer when you do it with part B. Let me give you another minute with part B. Okay, anybody still need more time on part B? So, if this is u, then du dx is 14x minus 3. And the original problem can be rewritten as y equals 2u to the 5th. And thus dy du is equal to 10u to the 4th. So this expression up here becomes dy du 10u to the 4th times du dx 14x minus 3, and then u is the 7x squared 2 to the 4th, and then this last thing times du dx 14x minus 3. So we get the same thing either way we do this. And give me a little feedback on this. Let's go back to the text channel. Tell me how you're doing, if both parts are you're equally comfortable, more comfortable with one part than the other, or whatever you're at. Okay. So this takes us looking at it two different ways. The way that's easiest to compute the derivative is part A. The way that kind of shows why the chain rule works is part B. Now, this part of why the chain rule works, right here, it seems kind of different than this, but you notice you're getting the same answer. All right. Now, why in the world do derivatives work like fractions and the du's kind of like cancel out and give you dy dx? That was an insight that Leibniz had, and he said, you know, we should use this notation that makes it look like a fraction so we can take advantage of that. And so here's an intuitive explanation of why this is always true. And it's kind of a crazy example, but it'll get the point across. Suppose y of t is the father's distance. It's a position function when running. You know, how far he is after t equals 1 second, how far after t equals 2, and so on. U of t is the pregnant mother's distance, position function when running, and x of t is 3-year-old's distance, position function when running. Now, we want to know how much faster the father is than the child. But there's a problem. The 3-year-old child knows he hasn't got a chance racing against dad, so he won't race against dad. So the child won't race against the father, but he will race against his pregnant mom. He figures he's got a chance against mom. So what we want is this dy dx. But what we can get is this. Dy du equals 2. Now, what does this mean? Now, the du's with the mom, the y is with the dad. The u is kind of the intermediary, although we want the relationship between y and x. If we can't get it directly, we can have any intermediary we want. And dy du, remember, this is the change in the output, change in y, every time the u increases by 1. So, if dy du is 2, that means when the mother goes 1 foot, the father goes 2 feet. It means the father is twice as fast as the mother. Now, we got the child and the mother to race. Now, the child was surprised. Pregnant mom was 3 times as fast as the child. Du dx was 3. Every time the child moved 1 foot, the mother moved 3 feet. All right. So then we could say now how much faster the father is, then the child. dy dx. Every time the child moves 1 foot, how many feet does the father move? This is equal to any intermediary can do. dy du, du dx. And he was twice as fast as the mom was 3 times as fast as the child. Multiply them together, the father must be 6 times as fast as the child. So imagine the child moving 1 foot, the mother moves 3 foot. For every foot that the mother moved, the father moved 2 feet. So 6 total feet every time the child moved 1 foot. All right, and we can introduce any intermediary. A cousin or an aunt would have worked as you. The equation below works because of a cancellation effect. It's that this and this cancel out, and then we still get dy dx. And so that essentially is what the chain rule is. When we look at it in this form, we can always do it in this form, but it's usually quicker to not actually formally set up, this is the u, and it's quicker to use it this way, but it could be done this way. All right. Any questions with regard to that? That's kind of, I want you to get this chain rule kind of in a, if you think about it a while, you can kind of get it into an intuitive way. This equation down here is always true, no matter what intermediary you use. All right, let's do number 2. This is a chain rule problem, but it's rather complex. Let me give you a little time for that. All right, I'm going to change this part, which is square root of 5 is fine, that's a constant, but the x I want to the 1/2 power. Square root symbol is fine around a constant, but around an exponent it's not good for taking its derivative. So I prefer it like that. Alright, anybody still need more time on number 2? Alright, so now let's take the derivative. All I focus on is the outermost function. I think of this as the tangent of something. So the derivative of tangent of something is derivative of tangent is secant squared. Of that something times the derivative of everything except the tangent, because we took care of the outermost function. Okay, now when I take this derivative, this is now e to the something. Think of just the outermost function. The derivative of e to the something is e to the something. Times the derivative of that something. Okay. Now this is why I wanted that to the 1/2 power, because it's easiest to take its derivative when it's written in that form rather than with a square root. So everything else is going to stay here the same. When I take the derivative of a constant times a function, I just take these two and multiply them together. I get square root of 5 over 2. X to the negative 1/2. And that's my final answer. I might, clean it up a tiny bit. Put the constant out front. The x to a power. You could put this as a square root and in the denominator if you want to, or you can just leave it like this. And there we have that. Alright. So, if you could give me feedback on this. Now this time, if you're having some difficulty, try to be as specific as possible as where the difficulty is. So if everybody give me a little bit of feedback. Okay, Francis wonders if there's a convention in the way to arrange terms, if you have trig terms and exponential. Not really. Some people put the trig terms in front, some people put the exponentials in front. Usually the simpler functions first and then the more complicated ones later on. Difficulty with negative exponents. Okay. All right. Let's go to number 3. dy dx equals 5. State what this means about the relationship between x and y, and then it's related to number 4. dy dx equals 5x. State what this means about the relationship between x and y. So do both 3 and 4. All right, anybody need more time on 3 or 4? All right, now, instead of going over the answers right away, I want you to go to your groups and compare what you have. So everybody kind of start typing in what they have for 3 and 4, and then see if you can kind of work out an optimal answer for your group, and then in a little bit I'll call on a group. Okay, anybody need more time still? All right, group 3, what do you have for 3 and 4?
Hold on, we're discussing.
Okay.
We're not sure about number 3.
Okay.
I would think that maybe it has a relationship with du or dy dau. That I think Bianca said ratio of dy du times du dx is 5.
Okay.
So maybe whatever y is, x will be 5? I don't know.
Okay, so what you're doing is you're making an analogy between this and what we did way earlier up here when we had this. When we had something like dy dx, which was the father being 6, that was possibly like if there was a u or something like this in there. And so if we had an intermediary du, it could add light on things. But even without an intermediary du, dy dx being 6, what does that mean? It means the father is 6 times as fast as the child. Okay, so now let's come back to here. Dy dx is 5. We don't know. X might not represent a child's speed or child's position function and so on. But what we do know is this is an instantaneous slope, dy dx. And what does slope mean? Slope means the change in the output every time the input increases by 1. So, every time y increases by 1, every time x increases by 1, y increases by 5, provided what?
It stays on the tangent line.
That's right, provided we stay on the tangent line. But now, this particular one, we don't need to put provided we stay on the tangent line, because it's just saying dy dx is equal to 5 all the time. Which means it's could have been a situation like this. Could have been y equals 5x plus 7. Something like this. Doesn't matter what the y-intercept was. The slope had to have been 5. And then every time x went up by 1, the y is going to increase by 5 dy dx. And if you took the derivative of this equation, you'd get dy dx equals 5. Right here. Is number 3 making sense? All right, let's go to number 4. Group 3, do you have anything on number 4? If you don't, that's fine.
So Bianca says, would the change in slope after the input changes by 1?
Say that again.
So then 4 would be the change in slope after the input changes by 1.
It's not the change in the slope, it's the change in the output when the input changes by 1.
So does that mean that dy is going to be 5 times as faster than x? Or, well, not faster, increases by.
Increases 5 times faster than x?
Yes.
That is the case on number 3, that the y is increasing 5 times faster than the x is. But this one has an extra x in it. So that also would have been my instinct. I would have just interpreted this the same way I interpreted this, except we have this extra x in there. And what in the world? State what this means about the relationship between x and y when it has this extra x in there. Now I want to open this up to anybody.
So whenever x increases, then y's output has to be 5 times x. 5
Very
times whatever x
good.
is.
Yes. When x increases by 1, the increase in y depends upon the current value of x. It will be 5 times the current value of x. Okay. So this one, it's trickier. And can you think of a function? Can anybody think of a function? Y equals something that when I take its derivative, I'm going to get 5x. It would have to have x squared in it, right? Because when I take a derivative of x squared, I get 1 degree lower to get it. What would the coefficient have to be?
It would have to be like something like 2.5.
Very good. 2.5 x squared. And then this one, the slope at any point depends upon the current value of the x. If the x is 2, what's the slope going to be right here? Anybody?
10.
10. We got the 10 by plugging the 2 in here. The slope depends on the current value of x. If x was 0, plug in 0 here, 5 times 0 is still 0. If we're at negative 3, the slope is going to be negative 15. It depends on where we are on the x-axis. All right. Yes, any questions, comments? All right, if no comments, let me go to homework and let's go. Let's just stick it here. All right, today's section we're going to be doing is implicit differentiation, and it's a lengthy one. So I'm going to limit the number of questions on the homework to 2. I'll do 2 questions on homework, and then if we have time at the end today, then we can return to more questions. I think there might have been one that was put in already. Somebody. It was number 56 on the homework. Alright, so let's look at number 56. This is just take the derivative. So I'm going to do a snipping tool. Alright, so I'm going to have my y prime be, and I think we got somebody's mic open. Let's just scroll through.
They fixed it.
Good. Alright, this thing, the outermost function, is something to the 7/4 power. Because that's the very last thing you would do. Like if x was 1, you'd cube it first, multiply by 4, take the cosine of it, and the very last thing is raise it to the 7/4 power. So this is going to be 7/4 times whatever this something is. Now raised, instead of the 7/4 is 7/4 minus 1, 7/4 minus 4/4 is 3/4. Times the derivative of the something. Now, we rewrite everything except the 7/4, because that's we've already taken out the outermost function, which we took into account already. Times the derivative of cosine of 4x cubed. Now, when we take this derivative, this is the derivative of cosine of something, which is the same as the negative sine of that something. Then times the derivative of that something. But the derivative of that is 12x squared. So y prime is equal to the negative and the 12 and the 7/4 all combined. Now, this 4 is going to go into this 12 3 times. So I'm going to get negative, the 3 times the 7 is 21. So negative 21. Then there's going to be an x squared from way back here. Cosine to the 3/4, 4x cubed times the sine of 4x cubed, and that's going to be it. Any questions on that one? All right, so I can answer one more question now before we go into the new section. And if you want to discuss, like if a few people have suggestions, we could discuss which one.
Professor,
Yes.
be able to explain how you got minus 21?
Yes. There's this negative sign right here. There's a 12 right here. And there's a 7/4 right here. Negative 3 times 7 is negative 21. Just combining all those coefficients. Any other questions?
I think there are several people who'd like 67, including myself.
67. All right. So y prime, or dy d theta, means the same thing. Derivative of the input with respect to the output variable. And I'm going to need what rule to start this off with? It's the product rule, because there's two different functions of x. Theta squared will be 1, and then all this will be the other. So it's going to be first times the derivative of the second plus the second times the derivative of the first. Now, if theta instead of x is throwing you off, you could always just rewrite the problem as x's. Y equals x squared secant of 5x. And then at the end, replace those x's back with thetas. It'll get you the same answer. So this is going to be, now the derivative of a secant of something is secant tangent. And then times the derivative of the something. When you take the derivative of 5 theta with respect to theta, you're just going to get 5. When you take the derivative of this one, this becomes 2 theta. So dy d theta is equal to, I'll put the 5 up in front, plus 2 theta secant 5 theta. And that's it. Questions or comments? All right, let's go to the next section. Let me copy this part again. Implicit differentiation. Put it right here. All right, now this section coming up. This used to be perhaps the hardest section in the whole class. But as I've taught this section over the years, I've been able to realize, the reason why it was so difficult is because it had 3 different components that students can get stuck on any one of the 3 components. So I created this worksheet that kind of separates and isolates the different components. And since I've done this, students have had great success with this section. So it's going to be no harder than the section prior to this, but it is kind of time consuming. So let's start out. Number 1, when do we need the chain rule? And which of the following need the chain rule, and decide with a yes or a no for numbers 2, 3, and 4. Do you need the chain rule? So I want you to pop over to your groups and see what your group consensus is on 2, 3, and 4, which ones need the chain rule? And I'll call on a group in a minute. All right, anybody need more time? So group 4, which of these needs the chain rule?
We came to the consensus that 3 meets the chain rule, but I'm also wanting a little explanation on 4, if that's okay, because the different constant is throwing me off.
All right, so you're pretty sure that number 2 is no.
No, yeah.
You don't need the chain rule. That's correct. And number 3, you're pretty sure that that's yes. And the reason why you need the chain rule on number 3, but you don't need it on number 2, is because, let me blow this up. When this letter right here exactly matches this one, when they're an exact match, you don't need the chain rule. You're taking the derivative with respect to x, and then x, something's happening to it. No need to the chain rule. But when this and this don't exactly match up, then you need the chain rule. Because they don't exactly match up, this part that I underline here is a function of that x. And thus it's a function within a function. So you have to have the chain rule to be able to do this one correctly. So if they match up exactly, no need for the chain rule. By the way, if you did the chain rule, it wouldn't hurt, because you'd take the derivative at the end of x with respect to x, which is times 1, which would be anything times 1 in itself, doesn't hurt. But here, if you failed to do the extra times 2, you'd have it wrong. You have to execute the chain rule at the end. Now, number 4, this, I'm glad you pointed out, this is the one, that's the tricky one. Do we need the chain rule for this? For what I've just stated so far, anybody want to tell me? They feel strongly one way or the other?
I think you would use the chain rule because you're taking the derivative with respect to x and you have a y here.
These two things don't match exactly. They have to match exactly to not have to use the chain rule. When this is not matching, what's the case is that y is itself some function of x. In fact, y could be 2x minus 3. And then you then would have, so y, and I'll be a little faster if I type this. Y is some function of x. It could be that y is equal to 2x minus 3. And then it would be exactly like number 3. And of course we need the chain rule right over here. And so if y is not a function of x, then we probably wouldn't even be interested in this problem. We really only ask these questions when y is a function of x. So the answer is a resounding yes. But notice how Sally was reluctant because this is new territory. What do you do when it's just a different letter than this one over here? We have to get used to this idea that that y is then some function of x. All right. So let me have you do these, which is practice using the chain rule. You shouldn't have any problem with 6, 7, but number 8 might be a little bit tricky for you. So do 6, 7, and 8 on your own, and let me give you a minute with those. Okay, anybody need more time for 6, 7, and 8? All right, let's look at number 6. You don't really need the chain rule. You just get 12x squared. The reason why we don't need the chain rule, because the constant gets to come out in front. Derivative of a constant times a function is a constant times the derivative of the function. And then the x and the x match up exactly, and it's just one thing happening to it. It's being cubed, so we can just take its derivative. This next one, we need the chain rule. 3 times 4 is 12. 3x minus 7 to the second. Then we have to chain on the derivative of the inner. The derivative of the inner is an extra 3. So then we get 36. 3x minus 7 to the second. All right, those two, hopefully you're very comfortable with those. And in this one, this should bring up some questions for you. You should be just as unsure about this one as you were about this one up here. Let's go ahead and try it, but we'll notice this letter up here and this was not the same, thus we needed the chain rule. This and this are not the same, thus we're going to need the chain rule. So I'm going to take the derivative of this. 7 times 3 is 21. Y to the 6th. But I need the chain rule because x and y are not the same. So what do I tag on to the end of this? Anybody?
Plus x to the 0?
Instead of being a plus, we're going to times. When we have a chain rule, we tag on something. And then it's always, let's look back at this one. What did we tag on for the chain rule? The derivative of the inner function. So we're going to tag on. I'm glad you said plus, because it makes us really focus that it's always multiply. And then it's the derivative of that inner function. But the inner function, what is the inner function? Well, it is y itself. Remember, y could be 3x minus 7 or something. So it's the derivative of that with respect to that. How do I write that? dy dx. It's going to look like that.
Is that it?
That's it. So this one has to have the chain rule, but the chain rule looks really strange. It's got this dy dx in it, but that's what's going to happen. We're used to, so far, all the derivatives we've done, it's been x's here, always just x's here. X's here, x's here. But in this section, we're going to have x's here and y's here. And when that happens, we have to tag along this extra dy dx. Because y is some function of x. Alright, so let's do this next one. Let's take this, we're kind of running out of space. Alright, take the derivative of this with respect to x. Now to do this though, we have to ask ourselves this question. Do I need the product rule? Do I need the product rule? Anybody?
Yes, you do.
And why do I need the product rule? Because there's an x and then there's a y, which we're assuming is a function of x, like it could be 3x minus 7. So there's two different functions of x multiplied together, so I need the product rule. So it's going to be first times the derivative of the second plus the second times the derivative of the first. And then I'm going to take these derivatives. And let me switch colors here. This derivative. d dx of y to the 7th. It's kind of similar to this kind of thing. Remember and with this we get a dy dx at the end. So we're going to get 7 y to the 6th times the chain rule, the derivative of the inner function. But y is a function of x, so let's do y dx. While this derivative is just 1. So then I'm going to get 7x y to the 6th dy dx plus y to the 7th. Any questions? All right, let's go to this next one. Okay. All right, take the derivative on number 10. And you're going to need the product rule. So go ahead with that one. I'll give you a minute. All right, anybody need more time? So it's going to be the first times the derivative of the second plus the second times the derivative of the first. Now the derivative of cosine x is derivative of cosine of anything, but notice the x and the y are not matching exactly. If they don't match exactly, then you have to assume that that's a function of that, so you need the chain rule. The derivative of cosine of anything is the negative sine of that thing. And then, because these didn't match, you have to tack on dy dx. The derivative of 3x with respect to x is just 3. So this first one is going to have a negative 3x sine y dy dx plus 3 cosine y. Now, if this is feeling strange, it should, because we have never done the derivative of y's. The derivative has always been of x's. And when you're doing this strange thing that we're doing now, derivative and there's y's in there, you're going to also get dy dx at times. It doesn't mean you just slap on an extra dy dx. Notice this term had dy dx in it, but this other term doesn't. It's only when you're taking the ddx of something that has a y in it. When the ddx of something that had an x in it, we didn't get an extra dy dx. So it's very particular. It's got to be done precisely this way. Any questions? All right. Give me a little feedback. Uncomfortable or comfortable with this? Just where are you at with these y's? Are you getting it, or are you still very confused? Okay. Let's take a 15-minute break, and then we'll practice with one more of those after the break. So we'll start again at 12:49. It asks you for the course ID?
Yeah.
And, but you got here through Canvas, right?
Yeah.
Through my
Course
math.
ID.
Okay.
Maybe I'll try them out the other thing.
Maybe if your instructor gives you course ID, maybe it'll work. Okay. All right, let's get started again. And we're going to go to number 11 now. And find the derivative, and it has x's and y's in it, and it's even more complicated. So I'm going to give you a minute with number 11. So it's going to turn out that with this first term, xy cubed, you're going to need the product rule. And then with the second term, x squared y, you're also going to need the product rule. So it's going to get a bit lengthy. Okay, anybody want to slow me down? Need a little more time? Let's go to this first one. This first term right here. I'm going to do first times the derivative of the second. Plus the second times the derivative of the first. Minus. Now, very important, we need a big bracket here. I'm going to get two things added together, but both of them are subtracted here. The subtraction sign has to go to both. First times the derivative of the second plus the second times the derivative of the first. All right. Every time that the d dx interacts with a y, see here it interacts with a y, here it interacts with an x. When it interacts with an x, you're not going to get a dy dx showing up at the end. But when it interacts with a y, you're going to get a dy dx showing up at the end. Here you're going to get a dy dx showing up. Here you're not going to get a dy dx showing up. So this is equal to, now we take this derivative and we're going to get x times 3y squared, and then chain rule dy dx. It's the chain rule because this and this weren't exactly the same. That's a function of that, so we have to chain it on. This derivative is just 1. If I distribute the minus sign, this d dx is the verb, the action. Take the derivative of y, and it just becomes dy dx. then this minus sign distributes over to here, minus, and this becomes 2x. I'm going to put that up front, and then a y, and that's all. And this I'll clean up. There's no like terms.
Professor, are you able to treat the dy dx terms as, like, could you join them and factor into, or
These two together, because this term and this term have dy dx in them.
yeah.
If they had exactly the same coefficients, see, this one has an x squared and this has a 3xy squared. So we're not able to combine them as like terms, but we could kind of like group those two together and say, well, I'll factor out a dy dx or something like that. That's possible. Yeah. All right. But this is what we would get at this point for this, for number 11. Any questions? All right. So that's one really important skill. How to handle these derivatives when y is showing up as something you have to take the derivative of. And it causes this extra dy dx to show up. Now, the next thing, and again, it's always renumbers. So let's just leave it. Number 1, review of needed algebra skills. Solve these following equations for dy dx. So this first one, get dy dx all alone. Tell me what dy dx is on A. So let me give you a minute for that. All right, anybody need more time? All right, so how I'm going to look at this is there's 4 terms. Terms are separated by addition, subtraction, or an equal sign. Now, 2 of the terms contain dy dx. Those 2 terms I have to get on the same side of the equal sign. All the other terms I group on the other side of the equal sign. So I'm going to, since there's this one is positive, I'm going to move all the dy dx's over to that side. And I'm going to get 10 equals 7 dy dx plus 2. Now, since I moved all the dy dx's to the right, I'm moving all the numbers to the left. So, and then I'm going to turn this equation around. 7 dy dx, I'll put that first. 10 minus 2 is 8. And then I divide both sides by 7, and I get dy dx 8 over 7. Any questions on A? All right, go to B. Solve for dy dx on B. Okay, anybody need more time? Let's look at this as 3 terms. And let me just check over here. Okay. So the 2 of these terms contain dy dx. So I'm going to move all those to the right hand side. So I can subtract 5xy dy dx from both sides. Now you might have moved them all to the left hand side instead. In that case you'd have subtracted 3y dy dx. And then you'd add 7 to both sides to move 7 to the other side. Doesn't matter, in the end you'll get what's called the equivalent fraction. So I'm going to get minus 7 is equal to 3y dy dx minus 5xy dy dx. Alright, so all the terms containing dy dx are on the right. All the terms that don't contain dy dx are on the left. Now I need to solve for dy dx. To solve for it means to write it one time and get it isolated. But how do I isolate dy dx when it's written twice instead of one time? Well, to condense how many times it gets written down is we factor out the dy dx. We'll factor it out from the right hand side. Now notice the 2 terms on the right hand side also have a y in common. But I don't care about that. I'm trying to solve for dy dx, so I'm just factoring out the thing I'm trying to solve for. So I'm going to put number, come on, I'm going to put minus 7 equals dy dx times 3y minus 5xy. And then I'm going to divide both sides by what's in parentheses. And I will get dy dx is equal to negative 7 divided by 3y minus 5xy. And I've solved for dy dx. Give me a little feedback. Just give me your comfort level with these 2 problems, A and B. All right. Okay, so let's go to C. Over here, let me copy and paste this. Or cut and paste it, get a little more space. Alright, solve for dy dx on that one. Alright, anybody need more time? Alright, let's look at this. There's, on the left hand side there's 3 terms, on the right hand side there's 2 terms. But altogether there's only 2 terms that contain dy dx. I'm going to move those two terms. Let's say I move them to the left. It doesn't matter. If I move this term to the left, then all the dydx terms will be over on the left. And then I would move these other terms to the right. So then what I would get is 2xy dy dx minus 7 dy dx equals 2 plus 5y minus 3x. And then dy dx is written twice. I need to write it just once. I do that by factoring it out. And then dy dx, I would divide both sides by what's in parentheses. And I would get that. Okay, so I am familiar with another technique now that we'll be using here is how to isolate dy dx. Okay, let's keep going. An explicitly defined function versus an implicitly defined function. All right. So if somebody says explicit, something is explicit versus something is implicit. Implicit it means implied. It's not stated directly. Explicit is it's out there, totally out in the open, everybody can see it. Okay. So when we have an explicitly defined function, then it really looks like a function because the output variable y often is alone on one side of the equation, and then you can replace the y with f of x, and then it really looks like a function. And that's what we call an explicitly defined function. An implicitly defined function is the output variable is not alone on one side of the equation. And for instance, an implicitly defined function, if I had 3y plus cosine of y equals 2x minus sine of x. To be a function, it just needs to have x's and y's in it. This can be a function. But can you solve this thing for y? Well, no, because this y is inside a cosine and this y is not. So there's no way I can't like factor out a y from both of these two things right here. I cannot get the y alone on the left-hand side of the equation. So this is what we would call an implicitly defined function. If it was missing this cosine of y, then I could just divide both sides by 3 and then solve this thing for y, and then it would be, if it can easily be solved for y, then we call that explicitly. If it can't be solved for y, then it's implicitly defined function. Okay, so everybody clear on those definitions, explicitly and implicitly defined functions? If there's no questions there, we're going to go and look at a problem. We're going to find dy dx when the equation is x cubed plus y cubed is equal to 8. And we will solve by using the technique called implicit differentiation. Note, we use implicit differentiation when we start with an implicitly defined function. All right. If this had been y equals something, we wouldn't use implicit differentiation. Since it's not y equals something, it's you know, the y isn't alone on one side of the equation, then this is an implicitly defined function. All right. Now, I'm starting with this one because this is kind of an implicitly defined function that could easily be turned into an explicitly defined function. So I'm going to be able to solve this two different ways. I'm going to solve it first using the technique of implicit differentiation. And then I will solve for y and do it a different way. All right, so let me just create some space here. All right, so I'll show how we can do this by implicit differentiation. And implicit differentiation, the first step is you take the derivative with respect to the input variable of both sides. So step one, take d dx of both sides. So this is the principle that in an equation you can do almost anything you want to one side as long as you do exactly the same thing to the other side, because that's what it means for them to be equal. Is almost anything you do to each side, the same thing as long as you do the exact same thing to the other side, you're okay. So I'm going to take d dx of the left-hand side, and that's okay as long as I also am taking d dx of the right-hand side. If two expressions are equal, then how they change with respect to x will also be equal. Now I'm going to simplify this. To distribute this derivative, the derivative of x cubed is 3x squared. The derivative with respect to x of y cubed is 3y squared. Did I forget something?
Do you have to put the dy over dx?
That is correct. How come we had to do that? Because this letter and this letter did not match up exactly. When they matched up exactly, like here, you don't have to do the chain rule. But when they don't match up exactly, you have to tag that up. The derivative with respect to x of 8 is 0. Everybody following? So now I am going to do that skill that we were working on before, which was isolate dy dx. So take d dx of both sides. Second step, isolate dy dx. So then there are two terms on the left-hand side. One term contains dy dx, the other does not. So I'm going to subtract that, move that to the other side. So I'm going to get 3y squared dy dx is negative 3x squared. Next, I am going to divide both sides by 3y squared to get the dy dx all by itself. So I'm going to get dy dx. The 3's cancel. And I'm done. I found the derivative. By the technique of implicit differentiation. And that's my answer right here. And it's a pretty simple idea. Take the derivative with respect to x of both sides, and then isolate dy dx. All right. Next, we're going to solve this thing again, but we'll do it a different way. We're going to solve this equation for y, and then directly take the derivative. We won't use implicit differentiation. So to solve this thing for y, I'm going to subtract x cubed from both sides. Y cubed is equal to 8 minus x cubed. And then I can either take the cube root of both sides, or my preference is to raise both sides to the 1/3 power. So if you raise both sides to the 1/3 power, power to power you multiply, you just get y. Now, why did I prefer raising to the 1/3 instead of cube rooting? Because when you want to take its derivative, it's a lot easier if it's in this format. Okay. Now this is the same function as x cubed plus y cubed equal 8. It's just rewritten so that it's solved for y. So we turned an implicitly defined function into an explicitly defined function. All right. Now, because we could do this, we would have never done implicit differentiation. The only time you really do implicit differentiation is when it's impossible to solve for y. When you can solve for y, you just do it. And you'll see why, because we're going to get a better answer when we do this. Okay. So now, I'm going to do dy dx. And I use the chain rule. 1/3 8 minus x cubed to the subtract 1, negative 2/3 power, then take the derivative of the inner function. But what's the derivative of, well, the derivative of 8 is 0. The derivative of negative x cubed is negative 3x squared. All right, now notice the 3's are going to cancel. And let me rewrite this as a negative x squared goes on the top. On the bottom is going to go 8 minus x cubed to the positive 2/3. Because negative exponent means bring it down to the bottom, like this. Okay. Now, look at my answer. dy dx is this. Compare this to the previous problem. The answers have some similarities, but they sure look different. Why don't they look the same? Well, the preferred answer is the one that we did second. Why is it preferred? Because it only has x's in the answer. So if I wanted to find the derivative when x is equal to 5, I just plug in 5 for my x, and voila, I get my derivative. when I'm over here, if I want to find the derivative when x equal to 5, I'm going to have to say, oh, before I can figure that out, I have to figure out what the y is when the x is 5. So I have to go back to the original equation, put the x is 5, and figure out what the y would be then. And then plug in both the x and the y into this to get my derivative when x is 5. So that's why this answer is preferred. But then you might say, hey, these answers don't look the same. But actually they are. Let me point out that, look, when we solved this thing for y, what did we get? We got this for the y. If you substituted 8 minus x cubed to the 1/3 for that y right there, then you'd have this thing squared, power to a power you would multiply, and that would give you 8 minus x cubed to the 2/3, and you see that that answer means the same as this answer right over here. But this is the limitation of implicitly defined functions. Implicitly defined functions, we weren't able to isolate. We only really use it when we can't isolate the y. And then the answer will always be in terms of both x and y, which is not the preferred form of the answer. It'd be better to have an answer that just had x's in it. But when you're doing implicit differentiation, this is the best we can do. So we take it. We say, all right, and then oftentimes we can use computers and stuff to help us out, so even though the answer isn't great, it's not that much worse. And it can be just as functional as the other answers. It's just more time consuming to deal with. All right. I need a little feedback here. Do you need me to summarize or to keep going on? Are you good with this so far? Or you need me to recap some high points or not? All right. So let's keep going. So, are the answers the same from both methods? They don't look the same. Show that the answers are equivalent? We can by just substituting this into there, and that shows that they are equivalent. When you take that and you stick it in here, they are equivalent. Alright, which answer for dy dx is better? Well, the answer in B is better. Because we want them all in x's. We don't want the answer in terms of the input and the output variable. Better would be just in terms of the input variable. But sometimes the best we can do is get it in terms of both. Alright, so this final note, in practice, we only use implicit differentiation when we're unable to solve for y explicitly. In this particular problem, we were able to solve for y explicitly, so in practice we would not have used implicit differentiation. But it was a very good problem for us to look at as our first problem, because we can see not only how implicit differentiation works, but what its limitation is instead of getting us an answer in terms of all x, we get an answer in terms of x and y. Alright. So, now that we have the basic idea of implicit differentiation down, let's do it on a problem that and I'm going to switch over because I'll be quicker and more efficient if I go to my whiteboard. So I need the camera. So we'll do problem number 1. Tangent of xy is equal to x plus y. We're going to do A, find dy dx. And then B, find the slope of this curve. At the point 0, 0. Alright, so first step. If I can solve for y explicitly, do it. But I can't in this case, because this y is inside a tangent function. The only way I could get outside of that would be to take the inverse tangent of both sides. If I take the inverse tangent of both sides, that gets this one outside of a tangent, but puts this one inside of an inverse tangent, which is just as bad or probably worse. So we wouldn't, there's no way to solve this thing for y. So the only way I'm going to be able to take this derivative is by using implicit differentiation. And remember, the first step in implicit differentiation is we take the derivative with respect to x of both sides. So we're going to do d dx of the left side and d dx of the right side. Now, the right side is going to be easier to do. So, we'll give ourselves a little room here on the left. Take the derivative of the right side, put your answer here. And then start taking the derivative of the left side, and I'm going to give you a minute to get ahead of me, and then you'll be able to see if you did this part right. But let me give you a minute now. Alright, so the right hand side, take the derivative of x with respect to x, I get 1. Take the derivative of y with respect to x, since they're different, I get dy dx. That letter and that letter didn't match up exactly, so we get that. Over here, this, by the chain rule, I think of the tangent of something. And then this is two different functions of x, because remember, y itself is a function of x. And so the derivative of tangent of something is secant squared of that something times the derivative. We have to chain along the derivative of the interior. Like this. Now, when I take this derivative, I'm going to need the product rule. First times the derivative of the second. d dx y plus the second times the derivative of the first. So this is going to become secant squared xy, and then this is going to become x. Now d dx of y is the same as dy dx plus the derivative with respect to x of x is just 1.
Mr. Shankin, I have a question. So you put y times d over d, the derivative of x. Wouldn't that just be y? Because you'd be multiplying y times 1.
I think you're asking, I'm not quite sure of your question. I think you're asking about this part. Is that right?
No, I'm asking about the other part, the second term.
Right here?
Yeah, wouldn't it be y because...
Oh, yes, you are correct. So, that is 1, and then 1 times y makes this a y. Thank you. And now I'm good. And then I have to now, so we did the first step, take d dx of both sides. Second step, isolate dy dx. To isolate the dy dx, well, I'm going to have to get rid of this parentheses first. So this whole thing has got to distribute to both terms. So I'm going to get, and I'm going to put the simplest thing up front, x secant squared xy dy dx. I'll put the dy dx away at the back end. Plus the simplest part up front, y secant squared xy is 1 plus dy dx. Alright, now I have 1, 2, 3, 4 terms. I want all the terms that contain dy dx, let's say we move those all to the left. And all the terms that don't contain dy dx will move to the right. So I'll get that. Then I'm going to factor out. So I have 2 occurrences of dy dx. Factor it out. And then my last thing, I divide both sides by what's in parentheses. And I'll get dy dx is equal to 1 minus so on. So that's the answer for A. We found the derivative, but there's always this limitation when you're using implicit differentiation, is that the limitation is your answer, unfortunately, has y's in it. We'd rather that not be the case, but that's the best we can do when we're doing implicit differentiation. Now, this is not much of a problem on this question, because they not only give us what the x is, they tell us what the y was. It wouldn't have been too hard to figure out what the y was. If you just figure out what the x is, you plug in the x here, and then the y would have had to turn out to be 0 anyway. But to answer part B, find the slope. Now, one of the ways you state this, here's the slope evaluated at. The vertical line means evaluated at 0, 0. That also could have been written like this: dy dx of 0, 0 equals. But oftentimes this notation gets used. Evaluated at. And then every time we see the y and the x, we substitute 0. Now, when we're substituting 0, we're going to wind up getting secant of 0. Now, secant of 0. Secant is 1 over the cosine of 0. The cosine of 0, 0 degree angle puts you over here on the unit circle. The cosine is the x-coordinate. That's 1. So the secant of 0 is 1. So I'm going to get 1 minus, I'm going to get y, which is 0, times 1 over 0 times, again I'm going to get the secant squared of 0, but that's going to be 1 squared, which is still 1.
Professor?
Yes.
The secant squared xy, could that just factor out in numerator and denominator, just leaving you 1 minus y over x minus 1? Would that work, or?
No, because in the numerator, the secant squared is on on one of the terms. If it was with both terms, then we could factor it out. Okay, and the same thing in the denominator. All right, but it's good to keep looking for shortcuts like that. All right, so 1 minus 0 is 1, and then 0 minus 1 is negative 1, and then I get negative 1. So that's the answer for part B. And we take a snapshot.
So I got the same answer of negative 1, but I took the tangent of xy, and I looked at tangent of x as one function, and then just the y as another function, and did product rule that way. Is that incorrect? Or, I still got something that...
Explain again. I'm not sure what you mean.
No, so I took, from the original tan xy, I actually saw it as tangent of x times another, like the function, or times y, and then used product rule and took the derivative, and it ended up giving me the same answer, but it wasn't...
So, from what I think you're saying, let me see if I'm getting this right. I think you said something like, you interpreted this tangent xy as tangent of x times y, something like that?
Yeah. So
Right. No, that means something very different. This tangent of xy, there's an implied parentheses. It really means that. So this would be something totally different. Now, if you wound up getting the same answer, I think it's just coincidence. It really needs to be interpreted like this. Which, I'm glad you brought up, because these subtle things are really important. that shortcut notation, they don't bother putting I took this right from the textbook. They didn't have the parentheses in there, but that's what it really means. Tangent of both of those. And it's something very different if you take one of them out of the tangent. Right here. Okay. Any other questions or comments on this problem? Okay. That's the idea in implicit differentiation. And notice the different skills that we needed to have. You needed to be able to isolate the dy dx, you needed to be able to take this derivative and get this dy dx showing up at the right spot. Let's look at one more problem. We're not going to have time to finish it, but starting it will be significant. Number 2. Y is equal to x plus 1 over y minus 1. Find y prime. Alright. Now, if we just jumped in to this problem blindly with following the rules, take d dx of both sides, we would make this problem much harder than we have to. If I took d dx of both sides, what rule am I going to need to use on the right-hand side?
The quotient rule.
The quotient rule, that's right. And the quotient rule is really complicated. And you wind up getting the denominator squared, this times the derivative of that minus that times the derivative of that over the denominator squared. And it's going to become a lot harder than you need to. So before I did that, I would try to make this equation a little bit simpler. Anytime you have a fraction, you can do what we call cross multiply. This times this is equal to this times this. Or you could think of it like this. We'd multiply both sides by this. All right. What would happen is, on the left-hand side, you'd get y squared minus y equals, on the right-hand side, these two things would cancel out. You just get x plus 1. This does not need the quotient rule. Way easier to work with. So, you don't have to blindly follow the rules that say, take d dx on both sides, so on. Think about maybe I can make my whole problem a little easier by doing something else first. This is what we call an equivalent equation of this. The solution of this is the same as the solution of this. So now we'd go to d dx of both sides. And this is going to be 2y dy dx minus, you take the derivative with respect to x of this one, minus dy dx. d dx of x is 1, d dx of 1 is 0. Oh, well, this one's we're going to have time to finish this. It goes pretty quick. There's a dy, and the next step is isolate dy dx. Factor it out. And there we go. So the homework is 3.8. Implicit differentiation. And I'll spot check that tomorrow. And Let me just quickly look on our schedule. Nothing special on our schedule. And a note that I've been looking at the prior homework. If you had no grade filled in from, let's say, a section that we did in the first week or two, and you still don't have a grade in it, I'm still looking at those. And if I, said, hey, you need to finish this or you need to make this correction, please do those as soon as possible. And then I will update your grade. Again, I'm trying to give everybody 10 out of 10s, but if you never put the correction in and I ask for it, you'll wind up getting a 0 for that assignment. So make sure you go back. Anything that no grade is showing up, after a little while here, I'm going to go ahead and put in zeros on those. I will change those when you get it in, but it's not going to look favorable on your average meanwhile. Any questions? All right, we'll stop here for today. I'll see you all tomorrow. And I'm remembering, yay, I have to stop the video.